So now in this video, we're going to look at the astable mode 555 timer again. So we're going to focus on the voltages across the timing resistor. So that's a 330 ohm resistor. This is a light dependent resistor. To get the capacitor to charge, current has to go through one resistor and then the light dependent resistor to charge the capacitor. To discharge the capacitor, pin 7 connects to ground and the capacitor discharges through one resistor. Since this is a light dependent resistor, unless the light is really bright, it makes up most of the resistance. Resistance gets very high as it's darker. So even though it's charging through two resistors, this one has so much more resistance that this one doesn't influence things very much. So that's 330 ohms. Because we're dealing with 6 volts, and we'll look at 6 volts will go directly across it at times. Whereas the 220 ohm resistors protecting the LEDs, we could use higher value resistors, but they have the LED drop. So they'll get a bit warmer if they have 6 volts directly across them. So I'll try not to wash out the flashing lights, but there you can see the closer that I get this, the faster they go. And if I zoom it in to a point, then they flash a whole lot faster. So there's less resistance now. And at this point, the 330 ohm resistor probably makes up most of the resistance. Maybe it's like 100 ohms for the light dependent or whatever. But any case, the main takeaway is we're going to look at the voltages. So you can see here I have the red alligator clip from the oscilloscope clipped to a jumper, same with the black one, and then those jumpers, which I color code, red for the measurement and then blue for ground. So this oscilloscope has the voltage at the red in relationship to blue. So normally we consider this blue one, the black clip there, ground, and then that's the voltage in relationship to ground. Sometimes it's more positive, sometimes it's more negative, and as you can see here, we have 6 squares going up. Each square is 1 volt. And now we will look at the current. So you're going to see that when the green LED lights up, current gets higher than when the red LED is lit up. So when the red LED is lit up, the output's high, the capacitor is charging, current's going through 2 resistors. When the green LED is lit up, the output is low, and at the same time the capacitor is discharging, but also at the same time the current going through that first resistor goes directly to ground. So that is when it has 6 volts across it. So we can look at that by zooming in and taking the blue jumper and putting it to pin 7 up here where the 2 resistors come together. And there you can see it went to 6 volts and now it is at ground. So we got 6 volts there, and so there's 0 volts across it. That's because the light dependent resistor has so much resistance. There's hardly any there. It's almost like a direct connection to the positive rail. So this is where it's going to get more interesting. Now I haven't done these tests yet, so this is actually I'm kind of seeing things the same time you are. So there you can see it's not going all the way to 0 because we're going so much faster. The light dependent resistor is now a low enough resistor where it's making a voltage divider. So we're getting a fraction of the whole voltage at all times right there. So that is the voltage across the resistor. Main thing is the first timing resistor. Main thing is sometimes this point is connected directly to ground. So you got the full voltage across that resistor. That is also when that capacitor discharges. Since both of their currents go to ground, this does not influence the speed of that capacitor discharging. So now we're going to take the primary measurement of the last video. But last video we had a fixed resistor here. Now we have the light dependent resistor there. So the voltage is going to be more interesting. Again, this connects to ground from time to time, and so we will just leave the blue jumper right there. We'll take the red jumper and put it to the other side of the light dependent resistor right there. And again, I assume you're already familiar with astable mode multi-vibrators. 555 timer versions of them. So in any case, there you can see it goes and then it drops to 0, but it's not going to 6. That is because voltage is actually alternating which direction it goes across there. And so I already have it select to that arrow. To select the voltage, you hit that button, or to select this arrow, which changes the divisions, you press the button again. So there's no arrows up there. I have to press this dial once. Now there's arrows up there. Turning the dial will go faster. So it just would take more turns of the dial to get up here. But in any case, 0 volts is where that little arrow points right there. And you can see that we have an interesting waveform that we did in the last video. It's taken longer though, because we're working with more resistance. We had two 1 kilo ohm resistors, 2 fixed resistors, whereas the light dependent resistor may be like 10,000 ohms, something like that, with this light level. And we can get it dark enough where it's hundreds of millions of ohms. And we can get it bright enough where it's practically 0 ohms of resistance, and then the only resistance would really be the 330 ohm resistor I have set for timing there. But in any case, we'll see that the voltage across here, so it's still alternating directions across there, but it's going a whole lot faster right there. That is the main takeaway. We could use a smaller value capacitor. So this is a 1000 microfarad, and we could use a much smaller one and it would go even faster. So if we used 1/10 the size, if we used 100 microfarad, whatever the light level is at any given time, it would be going 10 times faster. So I think this one's pretty good because you can actually see the LEDs flashing pretty good even with a pretty bright light on there, right there. And you can see the voltage has changed there. And so I think it would have changed more dramatically if this was a more accurate oscilloscope. So now we're going to look at one more thing before we go. So at the moment, the capacitor is discharging. Now it is charging. And you notice that when it changes from charging to discharging, there is a shot to a farther range from the 0 volt reference point, and it gets slowly closer towards 0, and then it shoots in the other direction. Way down, and then it works its way towards the 0 volt reference point right there. Again, because the capacitor is charging one direction, discharging in the other. So current is alternating its direction across the light dependent resistor, and so is voltage. And the reason why it has a bigger voltage difference at first is because it was discharging until it got to the point where it starts charging. And when it starts charging, that's right when it starts charging, that's when there's a biggest voltage difference between the positive supply and the capacitor. It works its way up to 2/3 of the supply voltage. As it gets closer to 2/3, the voltage difference is less between those 2 points, and so there's less voltage difference across the light dependent resistor. And then the light capacitor gets to 2/3 of the supply voltage, it changes to where it starts discharging. And at first, that connects to ground, that's 2/3 supply, so there's a biggest voltage difference at first, but it goes lower as it gets down to 1/3 of the supply voltage. So that's why you have a big voltage difference in relationship to ground right when it changes states. But it gets closer to ground as time goes on until it flips states again. So hopefully that made sense. But in any case, check out one of the other videos. Make sure you click like, subscribe, the bell, check out all the links in the description below. And if you can, donate to Patreon. I put a link down in the description. That would help out a ton. I will see you in the next video.